This tutorial demonstrates how to use GLFW's keyboard, mouse and joystick input. It also shows you how to toggle between windowed and full screen mode, and how to set up GLFW's window user pointer to use within callback functions to access your various game state class variables and functions for when processing events from the event queue. I'm continuing on from the previous tutorial, which demonstrates some of the techniques used for casting shadows in OpenGL, but it's worth noting that the code structure as presented here, in particular the callback functions class and the window parameters class, also applies in principle to all of the previous tutorials in this series. There's also a new player class, but apart from that, the main CPP file now contains less code than it did before, and all the other classes and both shaders remain exactly the same as in the previous tutorial. I'll start by showing you that I've now moved some of the code from the main CPP file's main function to the new window parameters class, which as you can see is all the GLFW and OpenGL initialization code. The advantage of reorganizing the overall program structure is that it makes it more accessible and easier to work with. The only additional code added to the main CPP file is the declaration of the callback functions class instance and the GLFW set window user pointer and set joystick user pointer function calls. It's the window user pointer that does virtually all of the work, so that's the user pointer I'll be discussing mostly throughout this tutorial. The window user pointer accepts two arguments, the first one being the GLFW window object, which encapsulates both the graphics window and the OpenGL context, and the second one being the pointer address of the callback class object. The callback class itself receives references to the game state objects that have already been instantiated, those being the player object, one of the light sources, and the window parameters. It's worth noting that the object being passed to the window user pointer doesn't need to be an instance of the class that also both initializes and contains the callback functions like is being done here for this tutorial. Within the constructor of the callback functions class, we set the callback functions, each which requires the window object and your chosen function name. Note that the parameter list for each callback function is predetermined, which means that you can't change them or add your own, but this is exactly where the window user pointer comes to the rescue. Because we already know the object type that was passed to GLFW set window user pointer within main, we can now declare a pointer of that type, and then static cast the pointer returned from GLFW get window user pointer to that type, which now gives us access to all the data members and member functions of the three game state objects that are data members of this class. Notice that all the callback functions have been declared as static, which means that only one copy of the particular function ever exists, but which is shared by all instances of the class, which corresponds to only one copy of each callback function being allowed, otherwise you'll get a compile error. Next is the fun part, because we can now control the game state objects in two ways, either by setting data members values directly within the callback functions, or by passing values to member functions of the game state objects that we now have access to. For keypresses, I'm modifying game state values directly within the key callback function, which includes setting various light source variables and also choosing between windowed and full screen mode. The light's position can be adjusted vertically, and it can also be rotated around the scene. You can also adjust the position of the near plane and the far plane, which increases or decreases the thrust and volume accordingly when the projection matrix is updated within the Shadow Maps class. Likewise, the light's field of view can also be adjusted. The following several callback functions each call a member function of the player class, passing in their callback parameter list values as arguments. The GLFW joystick user pointer currently has a bug, and so as you'll see shortly within the player class, joystick connection is all controlled locally within the class. Within the window size callback, the player's update projection matrix function is called to correct the aspect ratio, which is required as an argument within the GLM perspective function call. The window size variables are also updated, which are used to restore the window when exiting full screen mode. The frame buffer size callback updates the frame buffer's width and height variables in pixels, which are then used by GL viewport within the draw call functions. Within the window position callback, GLFW get window position is called, which updates the window's offset position values. Now let's take a quick look at the player class, starting with the constructor. Notice that apart from the two joystick function calls, everything else has been moved to here from the main CPP file, There are also now a few additional variables which are used to process the keyboard, mouse and joystick user input. The joystick connection event function simply checks to see if a joystick is connected. By default, the mouse axes and key presses control the camera yaw and tilt, but as soon as a joystick is connected, it overrides the yaw and tilt values to take control. The process joystick function checks to make sure that valid data is being received and then processes the joystick axes array values, followed by processing the joystick buttons array values, within which the yaw tilt rotate around center function and camera zoom function are called. The yaw tilt mouse value function simply calls the yaw tilt transform function, passing the mouse axes values as arguments. Likewise, the yaw tilt keys function also calls the yaw tilt transform function, but passes the rotation rate value as set and called from within the main loop. Notice that the GLFW getKey function polls the system to acquire the last reported key press state, in contrast to receiving input from the event queue as accessed within the various callback functions. A disadvantage of polling for the last known key state is that if you very quickly press and release a key, such that both pressing and releasing occurs after the last polling call's processing is complete, but before the next polling call starts, then the key state reported will be key released instead of key pressed, and therefore your game will have missed a key press. The yaw tilt rotate around center function simply keeps a rotation matrix to be rotated in one direction or the other around the y-axis, depending on which of the two button presses it receives. The yaw tilt transform function is where the player's camera gets rotated and translated within the game's scene. The first step is to rotate the camera target x-axis rotation matrix by the mouse or joystick X value. When a button is pressed to rotate the camera around the scene's center, the first step is to set the view direction as looking into the screen, by subtracting the position from the target instead of the target from the position. We now have -z as looking into the screen, -x looking to the left and -y looking downwards. Consider that at any given time, the camera can be anywhere in the scene and looking in any direction. I wanted to make the camera rotate gradually towards the centre when a button is pressed, but because the projected view direction can be either clockwise or anti-clockwise of the projected camera to centre direction, and then also that the dot product is always a positive value unless the angular difference is greater than 90 degrees, then how can we tell which side of the scene's centre the view direction is pointing? We can't just simply check if the camera's X position value is negative or positive as a solution, because the camera to centre angular position won't be parallel to the Z-axis if the camera position has changed from its starting point. Therefore, it helps to have a normalised situation for comparing their angular difference, which can be achieved by first rotating a copy of the view direction vector by the angular difference of the camera to centre direction and the Z-axis, and then checking the camera's X position value. But before all of that happens, the rotation of the camera's position around the scene's centre needs to be applied, and also the initial yaw view angle controlled by the player, because they will affect the view direction which is used in measuring the angular difference. After reversing the direction if required, and also applying some softening, all that's left to do then is to rotate the view direction matrix by the rotation spin factor that we've just calculated, so that the player's camera constantly points at the scene's centre. If we're not rotating the camera around the scene's centre, then instead we simply rotate the view direction matrix by the mouse or joystick Y value. Next, we make the camera's target X and Y values equal to the camera position X and Y values, but set the target's Z value to a negative value relative to the camera position. We finish off by creating the complete transformation matrix, by first translating the camera's current position to centre, rotating about the X and Y axes, and then translating back to the camera's current position. And then finally we apply this complete transformation matrix to the camera's target, which rotates the camera target around the camera's position. The camera zoom function simply adds the view direction's unit vector to the camera's current position.